Good morning. So we're going to start today's day with two fascinating talks. And the first talk is by Professor Matt Hansen from University of Maryland. I have to say a few words about Matt because Matt is one of the persons that I most admire in the field. For many years, people working in biodiversity science have been complaining that we cannot get a decent land cover change product. And there has been many challenges and many failed attempts at producing global land cover changes over many years, let's say over the last 15 years at least. And by the late 2000s, around 2010, 2011, I already heard people saying, well, that cannot be done. You cannot do that globally. It's not going to be solved. And Matt and his team cracked this problem, produced a wonderful global forest change map from 2000 to 2010, and published that study in Science. It's a 30-meter product, the first of its kind. And not only did that, made all this analysis and data immediately available on the internet. So anyone can download it, can use it, and many projects are now working with data that was produced in Matt's lab. And so it's my great pleasure to introduce Matt, and I hope he tells us that what is the next big problem he's going to crack. Thank you. Welcome, Matt.
Hello. Thank you, Enrique, and thank you for including me in the session. I'm going to give an overview of what we're doing. I say in support of biodiversity monitoring. I think that the idea is that land change dynamics impact biodiversity, impact a lot of our ecosystem services more broadly. So it's really not a biodiversity-specific application, but something that can inform biodiversity monitoring. I'll start out with a little bit of history. In 1994, 95. The first global land cover map was made in our department, University of Maryland. It was a 1 degree by 1 degree map, and 360 pixels by 180 pixels. And this was in the peer-reviewed literature. It was like, wow, what a milestone, super cool. And this was mainly to support climate modeling community, and we still do. I'll zoom into a pixel of that in Arkansas, United States of America. And there it is. That's a mixed leaf type forest in Arkansas, 1 degree by 1 degree. But NASA had projects, the Pathfinder project with AVHR, which is a meteorological satellite, but they tried to turn it into a land monitoring tool. Then MODIS was launched, which had land bands. So we started working with AVHR. We went from 8 kilometer to 1 kilometer. Now we start seeing some towns and other features. MODIS at 200. Oops, I'm going the wrong way. MODIS at 250 meters, similar thing. But at 250 meters, at least we're getting down to the scale where we start seeing land change. The big agri-industrial changes are pretty clear. The big fires are clear. But the whole time, since 1971 or 2, there were Landsat instruments. The longest archive is Landsat. It's a 30-meter polar orbiting satellite. But they made us pay for the data. And we used to always say, scientists get the data they can afford, not the data they need. And it was always this barrier to doing real science. You used to do a PhD with 1 Landsat image. Those were the days. You missed it. You missed the opportunity if you're young. But when they open up the archive, you're like, there you go. We got 1 million images. We can process them all. So you have to so that's another problem. We have to have a convergence of both. All of a sudden, they get rid of the pay-to-play, data policy. But we really have to have big computing. And you have to have the algorithms. But we had the algorithms because we were doing this basic. I've been doing the same thing for 20 years. It's literally the same thing. I mean, it's kind of boring. But going through this series. So now we're at 30 meters. So at 30 meters, now we see that this landscape has a hardwood bottomland forest that is largely kept alone, and then the upland is this churning of forestry land use. And at 30 meters, we've got the change. So that's the change of this landscape. you'll never see this change at 8 kilometers because half the pixels always turning over a 10, 15-year period. So now, and I remember because we were in Maryland, DC, the big NGOs, WWF, whatever, they come out and see us, and we were mapping these big pixels. They'd be like, I'm not interested. You know, it's just too blurry. It's not working at the landscape scale. Well, this is. And so, like Enrique said, really, I mean, our application space and our kind of customer base really blew up a lot in the biodiversity realm, in the habitat monitoring realm. So that was cool. So that's kind of where we are. We have Landsat data operationally acquired. And I think one of the big things for me, if we're going to do this work systematically with baselines and understand trends, and I think Enrique's point, the first point of yesterday's talk was about gaps, geographic bias, gaps in spatial domain. Well, to do this stuff and remove those gaps, we have to have systematic acquisitions. They have to be available, accessible, and then we have to just really have them ready to use off the shelf. So I differentiate, let's say, research from operations. And oddly enough, we're trying to get in this mode of operationally producing these products like forest loss every year. But it's really, and I don't know who's supposed to do that at the global scale. Is it FAO? Maybe. FAO has taken a beating for the kind of data they've put out with, because they're a member organization, and every country submits their own forest information on extent and change, and the definitions don't match. They had a meeting, and they came up with 800 definitions of a forest. So you can't really put these data together. They're not spatially explicit. You get a table. So there's this whole thing, how do we improve upon that? Who's going to do it? I think that's an open question, really. Because the University of Maryland's not going to be shouldn't be doing this 10 years from now. But that's the kind of point, that these data are ready to go, off the shelf. We can implement it at global scale. And it's a whole series. I would just point out, look at the data richness over time. And how, from establishing a baseline, it's hard to establish a baseline if you have inconsistent historical records. So this, although Landsat's awesome, it's really highly variable over time. And now we're in this golden age of Landsat 7 in gray and Landsat 8 in yellow. And we're getting over a quarter, well over 250,000 images per year globally now. Sentinel-2A, which is a Landsat-like, Europeans may not like to hear that, Landsat-like instrument. A nice compliment to Landsat. But that you stream in here as well. And now we're going to be getting sub-weekly Landsat data. That's awesome. But again, it's weird for baseline information, but we are in a golden age. I'm not complaining. So our approach is to just do this processing automatically on the pre-processing side. So we'll have an image, and we go through a certain series of radiometric normalization, QA, and we get rid of data that we don't need. And in the end, we just process every pixel automatically. And so this is a big data problem at the global scale. I mean, we have 9 petabytes of storage in our lab. We also do partnerships with Google Earth and Rebecca Moore's team. But this is I guess the hard part. But it's also if you can just kind of automate this side of it, the characterization that follows is made a lot easier. So that just gives you kind of a feeling for this is Real province in Sumatra. So in the end, we can process cloud-free global Landsat time series. And when you have a nice radiometrically normalized time series data, you can see the land cover. You can map it. And so that's what we do. And so we're working on a number of themes. The science paper was about, this is a paper from that, it was about where trees are staying as trees, where they're not being changed, where they're being lost, where trees are coming back. The Soviet abandonment of collectivized farming is one of our biggest gain landscapes. And then the pink is both, so where you have loss and gain. So these are typically forestry landscapes. So there's IKEA from space, and this is the southeast U.S. This place, our government paid farmers to get out of the business of cropping, row crops, and because it's kind of clay soils on steeper slopes, and they paid them, and they put in trees. And now it's we have the corn belt here with no trees, and we have the tree belt in the southeast now, and it turns over every 15 to 20 years. And one of the interesting things here, we have a new, and this is what's, I mean, what the satellite does, it sets up baselines, and then it also lets you, see inflection points. Was there some driver or some policy that interfered with the dynamic? And one thing we're curious about in the U.S. is the senator from Maine just has a rider on a bill that is that says in our new clean energy plan to call wood pellets and biomass zero emission energy. So if you have a hardwood forest and you clear it for wood pellets and you assume in 80 to 100 years that biomass is coming back, even though it burns dirtier per kilowatt than coal, that's the same thing as a solar panel. That's what that bill says, which is crazy. So our old growth, well, it's second, I don't mean old growth, but 100-year regrowth of hardwood forests, that's all this stuff in the mid-Atlantic. That's perfect for this bill. And you'll see. And even now, in the bottomlands of the Southeast, which have been, and they're hardwood, we're seeing more clearing. They're feeding these wood pellet plants. So that's, I mean, it's just super cool stories, and if you go online, we have a visualization of this. You can pan down to any 30-meter pixel and see stuff. So, can we relate this thing to different things? Obviously, biodiversity is one of them. So then we're doing trends in disturbance. So this is a reflection of policy. If we look at the arc of deforestation in Brazil, you see this color bar, yellow being early 2000s, warmer tones later, it's all yellow. And that's really reflecting the Brazilian policy to slow deforestation in the legal Amazon, in the humid forest of the legal Amazon. Around 2004, 2005, we started seeing the drop, and that was a multi-sector policy related to including big ag, not sourcing soybean on newly cleared forest lands. And that's so Protus, and Brazil gets tons of credit. They lead the world in this kind of official monitoring domain. The Protus product showed the extent of the problem, and then when they did the policy, it showed the success of the policy in slowing deforestation. I'm going way too slow. So then we do trends, and this is kind of interesting. And one of the big criticisms of our product was its gross dynamics. So again, like IKEA, the clearing in Finland is not the same as the clearing of a dipterocarp forest in Indonesia. So a lot of our work now is to add context and bring this story into a more complete from-to categorization. Is it burning? Is it being cleared? That sort of thing. So this is an example. Indonesia just dismissed our product because they said, well, that's just business as usual. That's our forestry sector. That's what we do. And you're mapping all of our forestry. And so I had a student from the Ministry of Forestry seconded to us, and she did a primary forest layer and broke out all the gross disturbance into primary, non-primary, and by landform, and showed that, in fact, primary forest loss was going up since 2000 in Indonesia, and it passed Brazil in 2012. And then we didn't hear so much from the government in Indonesia. So this is kind of a trend of the three big forest countries in primary forest loss. So what I mean by showing this is that now we're bringing context. So now we've made a baseline primary forest layer, and this is the good high conservation value forest, and these are the trends. And Brazil goes down, Indonesia goes up, passes Brazil, even though they have less than a quarter of the good forest that Brazil does. And then DR Congo's coming up, and you can kind of see it kind of converging here. What's really amazing about Democratic Republic of Congo, there's no agro-industry there, very little. So all of this change is really palm oil in Indonesia, soybean and beef in Brazil. Here it's 80 million people feeding themselves. And the intervention there and the threats to biodiversity are really, really big because their population's right up against the forest, whereas in Brazil it's all, remote owners from Sao Paulo and that sort of thing. So I think that's kind of interesting. And when you look at Congo Basin in general, look at DRC, it just jumps out at you, right? 80 million people feeding themselves. There's no food aid. There's no oil to trade for cheap food. There's war. It's the deadliest conflict since World War II, all that kind of stuff. And look at the other countries. Republic of Congo, Gabon. There's more people in Kinshasa than those two countries combined. So the pressures are very different, and the dynamics are very different. And the biodiversity. So Mike Fay, you know Mike Fay, the National Geographic, mega transect. He walked across Central Africa. He walked from here to here, basically. He avoided DRC. All right, so adding to context, so one of the things that we're really working on is we have this gross change. So, what kind of forest was it that was changed? What was the change factor? And then what was the fate of that forest? This is our next thing. How do we attribute really contextual meaning to the gross dynamic? This is just an example of mapping fires. And so the idea is in the high Arctic, tree cover loss due to fires. We see the climate signal meaning, resulting in bigger fires, more frequent fires, fires of larger extent. And so you can see this Fort McMurray. Is that right, Mike? So you've got this big fire early in the season. What's going on there? And so the climate signal is a big deal. And one of the things I'm really interested in, when we start breaking down the gross forest cover loss by these things, I think the climate signal is going to be a bigger disturbance factor over time. We see the big droughts in the Amazon leading to mortality. We even see tornado tracks in the southeast U.S. When I was growing up, there were no tornadoes in the southeast U.S. So we see this climate signal impacting forests and the pine beetle outbreaks in British Columbia and Colorado and South Dakota are another example of a climate disturbance. We also try to track structure. So this is a weird one to think about. We're mapping cover and height and other intactness as generic. You could think of these are like it's really like an EBV. So something that is continuous and it has some meaning in terms of ecology and habitat. And it's weird, but with Landsat, we can get between 5 and 25 meters very well calibrated, and we can do time series of heights. And that's another product. And so when we look at heights in Africa, we get this cluster of 3 groups, primarily 2. But this is this idea of, I think Carla Staver wrote this paper on alternative stable states. That's an ecological term. I don't know what it means. But she talked about this idea that the savanna is this derived landscape and sustained by fire, and it creates this step function between this open, canopied, mixed grass woodland thing, and then you go up against a wall of the rainforest. It's not a transition. It's like an abrupt thing. And this height map really captures it very well. So we try to use Landsat and leverage it with other instruments. So LiDAR's one that we like to integrate with. We haven't done much integration with radar, but that's obviously has some advantages because we are limited in some places with persistent cloud cover. Just in that example of heights, we can't go beyond 25 meters, so LiDAR and/or radar would be good. I'd like to just give a mention of like JEDI. JEDI is an instrument that'll be on the International Space Station and will be not quite global coverage, but a systematic vegetation canopy LiDAR instrument that'll give us really, really great quasi-global coverage. And it'll meet our kind of criteria for use. Another product that we do is we map intactness. So I'm just talking about different attributes. So like height, cover, intactness is another one. So intactness is where are the forests in the world that are absent of human footprint, where they don't have roads, and it's gone. Got some bad news. Forest is gone. All right, so usually with remote sensing, you really rely on the figures, to communicate. Now I have to talk. This is brutal. But intactness is cool because it's the high conservation value forest. I was just in a meeting in Brazzaville, Congo, and some of the slides we're going to show is the Forest Stewardship Council passed a resolution that said, let's see. I don't have my glasses on. Here we go. All right. So this is this idea, and we have different ways of mapping intactness. Intactness, I think, is a open research question. This is a very conservative definition. Any road, anything historical, any footprint that we could see from space, it's out of here. And we look for the parts that are left. What's interesting is this is kind of the opposite of that gross dynamic in Central Africa, and it's because they do so much logging in Gabon and Republic of Congo. And under our definition of intactness, those forests are out because they've been selectively high-graded, all this kind of stuff, so they're different. But there still are a lot of good, a lot of like the gorillas and whatever, they're still in these forests. But one of the interesting things from a policy perspective is this Forest Stewardship Council has a policy motion that says if you have a concession and you're certified, and we find intact forest landscapes in that concession, 80% of it must be set aside. That's a huge thing. So now the concessions are saying, I got to give up 80% of my future profit. And the government says, we got to give up 80% of our taxes from that. And this is for Russia, for Canada, whatever, and it's a big deal. But why am I mentioning this? But the objective is to somehow incorporate this remotely sense-derived product into conservation and to try and save the last bits through the companies that are behaving in a responsible way. And that's kind of cool. So our per pixel mapping nests into this change, and as we move forward, you see we spill out, and we're going to remove this intact forest. This is 2014. 2015, they leave this area. They go up to a new whatever you want to call it, unit of the concession, and they start exploiting up here. And then this year, we have a near real-time alert. There are fires here. So the El Nino really dried out these forests, and they burned. I don't know what the fire return interval is in these forests, but it's centuries. And this is basically along these roads. So who's responsible for this? This is all Marantaceae forest. It's all gorilla habitat. Looks like this. This is a gorilla nest. And this all burned 26,000 hectares. What am I saying that for? Well, how does the company respond to this type of event? And the people are going out in the field at the end of this month to take a look. And nobody's going to take responsibility for this. The company will say, well, the villagers from over here burned it. You can't do too much forensic work. But this is, again, I think that working in these landscapes of the last intactness and trying to figure out what's going on, what the pressures are, is really interesting. So when we do this work I'm transitioning now to another application, near real-time monitoring. Our current product is every year we update and we do a new map. So each of these colors represents a new year. Ta-da! And so now what we're doing is we're working on near real-time monitoring. So we want to do it every day, but every week we're giving a new layer. And we're doing this initially for Republic of Congo, Peru, Brazil, Indonesia, and Far East Russia. And the cool thing about it is when this is a cool product, because when you go out there, you're right there at the site just days after the activities occurred. So this is what it looks like, on a pseudo-weekly basis. This is Peru, and we're just populating the image, and you'll see a logging road come in from the south, and then it'll be extended, and you'll see the selective extractions off to the side. And this has been met with, in Peru, they're delivering it to certain programs in the Ministry of Environment, also with their enforcement agencies. So Brazil, again, I'd like to pump up Brazil all the time, but Brazil is the only country that has done slowing of deforestation, but a lot of it had to do with enforcement. So it's like they have a land use plan, they have the capability to monitor, and then they enforce when they see something wrong. And Peru is showing some examples of doing that as well. In Russia, we have an example of using this, and this is interesting. So in Far East Russia, this alert product has been used, and they go out and they've met illegal loggers. And when they talk to them, they get feedback. This is, the loggers will say, yeah, you found that one where we took trees, but over here, we took this when you missed it, right? And they're like, yeah, okay, good. They're figuring it out, right? And then the people in WWF were saying a week is too slow. When we go out there after a week, they're gone. So they put up camera traps because they go, but they leave the logs, and they have to come back to the logs to take pictures and stuff. Then you can imagine the loggers saying, no, let's smash those camera traps. So there's this interesting thing in terms of like when illegal loggers understand the technology, they can change their behavior and try to hide essentially. We're seeing that in Far East Russia. Okay, this is one example that I think is potentially of use with biodiversity, and the idea is, the cool thing I think the satellite does is it tells you where to look. In addition to mapping's great, but we can't do every variable from space. Like we can't do species richness, typically, from Landsat. So this is an example for carbon, but the idea is we have strata that are associated with structure and intactness. And these strata are places where we could sample. And when we sample there, we will find different things on the ground. We'll certainly find different carbon stocks, and you'll certainly find different, probably other biodiversity ecosystem services. So within each of these strata, there are dynamics. There's a certain portion of this really good stuff, the dense cover, tall, intact class. When it gets cleared, There are different impacts versus what happens when a savanna gets cleared. And so we throw samples, and these samples are stratified in a way that they follow the satellite signal. So all the reds, that's the arc of deforestation, are in what we would call natural forest being cleared. All the blues, like southern China, that's just managed forest, so forestry. And so in Indonesia, it's a mix. Just to keep in mind that, this goes back to Enrique's point of geographic bias or geographic gaps in our knowledge. When you use this kind of approach, you have inclusion probabilities everywhere, but you're stratifying and targeting your themes of interest, and then you go. And so you can imagine doing biodiversity surveys based on this kind of information over time and showing, in fact, trends that the paper Enrique referred to did not show because the data are opportunistically or super biased in the way they're collected. Okay, how much time do we have? 5 minutes, okay. So this is an example from in the field. In the Yucatan, this is a stratification based on disturbance, and we go to visit these places. And again, when we go in the field, we could do carbon stock, we could do whatever variable we are interested in. But what happens is, even though we start with a gross forest cover loss product, we get 80% of that loss occurring in rotational systems. So they talk about the Yucatan Peninsula being in a state of arrested succession. It is just this smallholder churning all the time, and it never really kind of, it's just a dynamic landscape. Well, 80% of all the change we saw was that smallholder type of land use, and 20% was deforestation. So sugarcane, corn, big ag. And we did the same process, the same work in the Chaco of Argentina, and found the exact opposite. 80% was deforestation. For pasture, they need more beef in Argentina, and row crops, and then 20% was rotation. Let me just skip ahead here. Okay, so I just want to highlight that we do different products. It's not just trees. We do agriculture. We do bare ground. So this is bare ground change. And when I zoom into a place like Dallas-Fort Worth, all these things, now this is a different kind of dynamic. It's gross bare ground change. And so we see urbanization. And in this case, all the urbanization is clustered around the airport. Those are the new central business districts of the future. I got a couple of examples from Germany. So this is Berlin. And the change is mainly the new airport, but other things. This is the bare ground gain dynamic. So we see urbanization, mining. This is in eastern Germany, big coal mine. And so when we look at these trends over time, so this is a different theme, but it represents an interesting, this is like collapse. This is typically very intensive conversion, denudation of the landscape. You can see that this really represents economic health of the globe. So in 2008, it peaks, and then we start seeing residential developments go down, all this kind of stuff. So working in different areas. This is a subset of that theme, and I go back to the Congo because I think it's really cool. When you look at settlements, which are what we would call a bare ground category, you can see where all the people are. They're all along the edge of the forest, not so much inside the forest. In the land use planning domain, we hope that countries think about this type of information because this is where their investment should go because that's where the people are. Don't build roads into the forest. That's not where you get, it's easy to make, but it's not the great, if you're committed to Paris and forest restoration, you need to work here. So we zoom into this area. We have like 3 states of stress on the environment. This is like super stress, short fallows, this is a protein deficient landscape. Here it's intermediate, and there they haven't, the populations haven't really exploited the landscape yet. So this is the city of Kikwit. And so mapping these things is like stresses on the environment, especially in places like Central Africa, really cool. And I'll just zoom through water. Water is another thing, 30-meter water. This is rice paddy evolution of water hydro period in northern Java. This is water in southern Africa, so the Zambezi, and Dr. Murray was talking about this yesterday, the Okavango. So this is February surface water, and then it collects in April this is the Bratzi Plain, and then it's gone in June in the dry season, the dynamics. So this is another theme of water. And in the end, we want to put all this stuff together. So I'll wrap up by saying that if we can do different themes and integrate them, now we have what was the tree cover, what was the change dynamic, what was the fate of the forest. So this green is row crops. And when we zoom into, We zoom into central Brazil, we have the Amazon basin and the Cerrado. This is all of the clearing for soybean, largely. If we look at the loss rates over this area, most of the clearing for soybean was in the early 2000s, and later on, it's out here in the Cerrado. So it's not like soybean just disappears. It moves out into the Cerrado. And so even though the policy was successful in getting it out of the high conservation value forest, there is no, there is leakage, and you get that kind of thing. So I'm done. I just want to make this point that, a lot of this is based on freely available data. We're excited about having Landsat and Sentinel-2 to get together. I'm concerned about pay-to-play systems that'll distract us and keep us in a researchy mode, but won't allow us to do things at scale. I'm really happy Planet is out there and, Earthcast and stuff, but I don't know how we monitor the globe with those data, because we don't get dense time series. We're not going to be able to afford it. So I'm kind of curious how that shakes out, because we're really interested in monitoring the planet and its health and all the ecosystem services that are at risk. So I think the public infrastructure is really important to that. All right, thanks.
So I think we can afford a few questions.
Thanks, Matt. I'm John Paulo Rodriguez from the Venezuelan Institute for Scientific Investigation in Caracas. Matt, how close are we from automated monitoring of non-forests?
Well, it depends on what kind of monitoring, but the land use that confounds me is pasture. I mean, stocking rates vary so greatly. I mean, what grassland in Africa doesn't have some cows on it? Western South Dakota is like 1 head of cattle per 25 acres. It's such a strange land use. So I think there are some challenges there. I think short woody cover, woody encroachment is also another challenge because of signal. What's going to help us a lot is having LiDAR data at scale that'll help us to calibrate models so that we can get better differentiation of structure in non-forest areas. And I think we have really good prospects of doing cropped area and type for food security applications, even in places like Africa with smallholder, non-intensive ag. I think that's a good growth area. But I have some troubles with kind of pastures and degradation and things. I think it's a cool research thing, but I don't have a good answer.
So in tropical forests, we have also natural gap creation. So is it possible to distinguish this with a remote sensing analysis?
That's a good question. When we, when we do our validation, I don't think that's something that really, we don't see that so much. On the other hand, when we look in the logging concessions, there can be a 30-meter pixel. If they cut a big tree and it falls over and it knocks over a couple others, we do see that. And I just, so I don't know the mix, but like windfall and things like that, very obvious. But kind of like that slow single tree type stuff, I think it's not clear to us. It's not in our data. I don't think so.
I would like to know if you have advanced in a way to detect or assess forest degradation or land degradation.
Okay, so degradation to us from the forest perspective is that cryptic part we can't see. So what we're trying to do is map directly all disturbance, and a lot of our disturbance is fractional. Like that example I gave you of a single big tree going over. We see that. That's not a clearing. So we're trying to get this idea that, beyond which we would say something is degraded. And right now, our degraded class is the fragments. We use clearing to model, and there was a presentation yesterday, and I think this is a normal thing. It's like when you bring an edge into the rainforest, there are plenty of studies that show there's a impoverishment of the forest close to the edge. So that's really, we use indirect methods to label what we think to be likely degraded places based on change. Not every edge is degraded, but when we see a thing come in, we assume that there's a buffer effect. That's the way we treat degradation right now.
So when this selective logging happens and you detect it, does it depend on how much time goes after the logging? Because then you have regrowth, and then
Okay.
it's getting tricky to
great.
detect it again. So what's the maximum time gap you can afford in order to detect it?
Right, so like in Brazil, we're doing this operationally looking. Brazil's typical method is look every July and August where they have an atmospheric window and they say, okay, do we see something? Well, if something is logged in September or October, they won't see it. But when we're looking at every possible pixel, we're picking up a lot more dynamics than they are, because after 3 months, it's gone. From an automated method, we'll miss it. So right now, by looking at every pixel and we're getting, nominally an image every 8 days, we have cloud cover that can hurt us. We see a lot more of these kinds of dynamics.
Okay, I think we have to stop there. Thanks again, Matt. Thank you very much.